we're going to take a look at one final example, and this example is going to kind of work with everything that we've seen so far with respect to input, output, file writing, graphing, those sorts of entities. So this is something that you might remember from maybe Physics 1, or for those of you that might have taken up through Calculus 3, you might remember seeing this formula that can try to predict what the height of an object might be after x displacement from the origin. All right, and the variables are many for this one. So we have the gravitational constant g. If we're in meters, the standard unit's 9.8 meters per second. So this is really just a constant. Initial velocity must be given, and then also an initial angle to which the object is either fired or thrown from, as well as an initial height, which y0. And if we know that, then the output is going to be y. And so one of the things that a computer algebra system such as MATLAB might help us to do is to be able to kind of visualize this, and also to kind of get an idea as to what how the angle, changing the angle, might affect the trajectory or the path of this. So I developed a problem here that says, suppose we want to explore how trajectory changes. We're going to use the above formula to write some MATLAB code. And what we're going to do is we're going to ask the user for an initial height and initial velocity. And just for convenience, let's use no initial velocity. I'm sorry, no initial height and initial velocity of 28 meters per second. And then what we're going to do is we're going to create a variable that has a row vector from 0 to 80. All right, and that's just basically going to be displacement from 0 meters to 80 meters. And we're going to use an increment of 1. And this is where we're going to start going through and seeing the change in the angle. So we're going to let the angle change from 15 to 75 in increments of 15. And then we're going to store all 5 of those variables. So we're going to basically get 5 new row vectors. And then we're going to write it out to an Excel file. And really, we'll only have 6 columns, right? We're going to approximate the max height, and we're going to write the max height in sheet 2. We're going to approximate the average height, and we're going to write that in sheet 2. And then we're going to create 5 scatter plots. We're going to use the subplot function, and then we're going to use appropriate titles to ensure that everybody knows what we're looking at. All right, so a lot going on with this one. So let's get to it. First things first, we need to ask the user for some input. All right, and so the first thing we're going to do is we're going to say that let's define v to be the initial velocity. So let's enter velocity. All right, and then the next thing we're going to do is we're going to ask for the initial height. I'm going to call that h, even though it's y0. So we're going to input, enter the initial height. We know the constant for gravity, so that's 9.8. And then from there, the only other thing that we need to do is we really need to find that row vector x. So that's going to be 0 to 80 in increments of 1. So remember this code right here, this 0, 1, 80, that just means initial, terminal, and incremental. So this is the increment, and then 80 is the terminal. All right. Now let's go ahead and compute the y value. All right. And remember, we're going to have, let's call 5 variables. So I'm going to call one y15. So that's going to be the angle at 15 degrees. All right, now here's the incorrect way to do this. So we're going to say, now our formula, and let me bring our formula back up just so that way we can see it. We're going to have tan of theta naught x minus gravity over 2 velocity square cos square theta naught x squared plus y0. So this is what I'm programming, this code right here, or this formula. Of course, we might start by saying tan of 15 dot times x. All right, remember it's a vector. All right, or it's a row vector. But we're not going to use 15. We're going to use pi over 12. All right. So be careful, because remember MATLAB starts in radian mode. All right. So even though it's 15 degrees, we have to use pi 12ths minus the gravitational constant divided by 2 times the velocity square times the cosine of pi over 12, and we're going to square that cosine value, and then plus the initial height, which is h. Now I know the height's 0 for this problem that we're suggesting. And oh, I forgot to multiply that by x squared. So dot times x dot square. All right. Some of you might be wondering right here why we didn't use the dot. Well, it's because v is a scalar or a constant, and same thing with the cos of pi 12ths. All right, so let me just go ahead and execute this, and I'm going to show you what happens, because if this doesn't execute, then we're probably not on the right track. So let's enter an initial velocity of 28. Let's say initial height of 0, and we get at least some values. Okay, and so this is what you should get. It's going to show all 80, or in this case 81, excuse me, because of 0. Right. Now, what I'm going to do is I'm just going to copy and paste this 4 times. And I'm just going to change this to 30 and 45 and 60 and 75. Right? And then instead of pi 12ths, remember 30 degrees is pi 6, pi 4ths, pi 3rds, and then 5 pi 12ths for 75. And then over here, I have to do the same thing. So 6, 4, 3, and then this should be our 5 pi 12ths. All right, so now we have our 5 row vectors. And if we look at our instructions, so we prompted the user for the initial height and the velocity. All right, we've created a variable that's a row vector, and we've computed y for each of these. Now we have to write those into an Excel file, and then we're going to title our 6 columns. All right, so we're still in step 3 here. So here's what we're going to do. We're going to make a variable header, and header is going to be equal to, and this is going to be our Excel file, or this is going to be our first part in our Excel file. Let's say the x value, which is really the displacement. So I'm just going to call it displacement. And we have our height. So we're going to have y height 15. Or we could just say height 15, if I could spell it. So we could have height at 15 degrees. And then I'm just going to copy and paste this a few times. So this is our 75, and this is our 60, and this is our 45, and then this is our 30. Right. And we can close this out, suppress it, and now we're going to use our XLS write. And just to remind you of the code for this, let's call this trajectory, XLS, and we're going to write out the header. All right, so now we're printing out the header. It's going to go in sheet 1, and we're going to start in A1. All right, so that's our syntax for this, XLS write. Right? Now the next thing we're going to do is we're going to write each of these, Y15, Y60, Y75. So we're going to write a code for that. So it's going to be XLS write, and we're also going to write X into there. So we have our 6 columns. So XLS write, and we still have trajectory dot XLS. We're going to write X, but not X. We're going to write X prime. Okay, so remember, X prime is the transpose. All right, so don't forget that you have to make sure that you flip it around. All right, right there, this is going to be a row vector. We want a column vector. All right, we're going to write it in sheet 1, and we're going to start in column A2, or in cell A2. Okay? And then from there, let's just copy and paste. And let me go ahead and suppress these so that way we don't get some messages out on the screen. Not that they're bad messages, it's just that they're not useful. All right, and we're just going to change this. So now we have Y15 prime, we have Y30 prime, Y45 prime, Y60 prime, and then Y75. Right? And then we're going to change these to B2 and C2 and D2 and E2 and surprise F2. All right, so let's run this. Let's see what happens. Hopefully we didn't make any syntax errors. And by we, I mean I. So initial velocity is 28 and 0. If it runs correctly, we'll see the trajectory XLS, which we do. Let's open this outside of MATLAB. and it might open today. Right. So right here, we have all that data. All right, so that's pretty cool that now this is basically our model for our trajectory at the 5 different angles. Now, of course, we want both a graphical and some sort of analytic summary of this. All right, so that is part 3. Part 4 is to approximate the maximum height, and part 5 is to approximate the average height. And this is to be written in sheet 2. All right, so this isn't too difficult. So what I want to do in sheet 2 is I'm going to make a second header. So let's call this header 2. And header 2 is going to be equal to, so we need the maximum height for each. So we're going to have max 15 degrees. Right? So our maximum at 15 degrees. And then we're going to have a max at 75 degrees. We're going to have a max at 60 degrees. We're going to have a max at 45 degrees. And then we're going to have a max at 30 degrees. All right. Then we're going to write this. All right, so I'm just going to copy this code because it's pretty close. And we're just going to change that to 2. So it's in sheet 2, and we're going to use header 2. All right. So now we have our 5 columns or our 5 markers. And now we actually just have to write out what the maximum height is. And the maximum height is just a function. So I'm just going to copy this animal right here. Right? And what I'm going to do is I'm going to write the max of y15. So that's the max height at 15 degrees. And we're going to write that in sheet 2, and we're going to write that in cell A2. All right? So that's going to be right under max 15. All right? And I'm just going to copy and paste this. And I'm just going to change these to 30 and 45. So this is 30, and then we have 45, and then we have 60, and then we have 75. Right? And then we have A2, B2, C2, D2, and E2. All right, so that's all our maximums. Now let's do it all again. And this time we're going to do the average. Right? So if I was to break these up just a little bit for clarity. So this section, remember, was for page 1, where we actually wrote out the raw data. This is page 2, where we have the maximum. And still in page 2, and I'm going to call this header 3, we're going to have the average height of 15, and the average of 30, and the average of 45, and the average of 60, and then surprise, we're going to have the average of the 75. Right? I'm going to write this in cell, let's say A4. All right, so I'm going to skip a row, and then I can change all of these to 5s. So this is 5. So I'm going to write everything below that. And instead of max, remember our function to find the average is mean. So I'm going to find the mean and the mean and the mean and the mean and the mean. All right, so excuse me. So let's go ahead and give this a go and let's see what happens. All right, so we have a lot of code here, and let's see if this works. So far so good. Initial velocity is 28. Initial height is 0. It might give us like that message because we're writing to another sheet, and that's fine, no big deal. Let's open this up outside of MATLAB. All right, and here's our data. All right, so pretty cool. So it looks like that the maximum, or this should be average. I think I should have changed these headers to average, but that's all right. We know what it is. I just have to change the titles, but this is the average height, and this is the max height. And sheet 1 still looks good. All right, so we're good with that. I just got to change these to, oh, I did that correctly. I'm sorry. I know what I did wrong. This should be header 3. All right, there we go. Most of you are probably screaming at me to change it to header 3. All right, so how far are we here? So we have approximated the max height. We've approximated the average height for each scenario. And we printed them in sheet 2. So all that's left now is these subplots. All right, so that's not too bad. So what we're going to do is we're going to make a subplot function. So we're going to say subplot 1, 5, 1. Just to remind you, that means that this is 1 row, 5 columns, first position. we're going to plot x comma y15. All right, so that's going to be all the data in x, all the data in vector y15, and I've been on this sort of upward triangular kick, so let's do that. We're going to have an x label. It does say to label it correctly, so this is going to be the displacement, and our y label is going to be the height. And finally, our title, we're just going to call that, let's call it displacement versus height for 15 degrees. And we could even call it trajectory if we wanted to. All right. One other thing I'm going to do, and we haven't done this in any of the videos, I'm going to turn the grid on for this one. All right. And that's just because the numbers are probably going to be fairly big, so it never hurts to have that grid. All right. So now we have that, and guess what we're going to do? We're going to copy and paste that 5 times. So let's just change this to 2 to 30, and we're going to change this to 30 degrees. And we're going to change this to 3 to 45, and then to 45. You can see that this is just repetitive, not difficult. So this is going to be 60, and this is going to be 60 degrees. And then finally, we have our 75. So position 5, and we're going to change this to 75, and we're going to change this to 75 degrees. Now, this just prints out the scatter plot, or hopefully it will, because we haven't executed it yet. So let's give it a try. Let's see what happens. So I'm going to run this. All right, so we have 28 meters per second. We have 0 meters. And this is just going to give us hopefully, the subplots scatter plots. But what it doesn't do is it doesn't print it out to a file, but no big deal. We'll see that in a second. All right, so here we go. We'll analyze this momentarily, but at least it does what we want it to do. It prints out all the scatter plots. It shows us a trajectory, like a pathway. And of course, it also gives us that Excel file. All right, so one last thing that we have to do, we have to print this out to its own file. So remember, we use the print function. I'm just going to call it trajectory. All right. And let's make it a JPEG file. So we're going to say -d_jpg. All right, so this should be the last line of code that we have for this. And let's see, let's run it one last time. And I noticed I made a capital EN here. Sorry. All right, so let's give it a run. Oh, one last thing I didn't do is I didn't close the files. So we have to F-close all. That way, if we want to delete it when we're done, we can. All right, so now let's run it. All right, so 28 meters per second, 0 is the height. And it's taking a little bit longer because we just introduced the print option. All right, so here's our file. That's cool, that's new. All right, so let's take a look at our scatter plot, which printed to the screen. All right, scatter plot's the same, that's good. Let's open up this scatter plot. Let's open up this Excel file. Make sure everything's kosher before we get out of here. All right, so here's our, so it's not all that great. I'm not sure why maybe it's just kind of not expanding, but it should look a little bit better than that. I'm gonna close it and try again. Yeah, down here it looks pretty good in this window. So let's open it again. So might have to use a different file or something of that nature, but regardless, we could just look at the scatter plot from the actual picture, which I might have closed already. But the Excel file, so notice that we have the maximum, all right? Notice that 75 degrees has the best maximum, but it has the lowest average height. and that means that it's going to hit the ground a lot sooner than the other ones. This one has the most average height, and it also has a relatively decent maximum height of 30 meters. All right, so that's pretty cool that we can analyze it a little bit. I'm going to run it one more time just so we can look at the scatter plot. Just to kind of compare what's going on with this. All right, so let's see what's going on here with this. All right, so even though the graphs look fairly similar, you have to look at the scale. All right, and notice right here, and also with the grid on, you can see that right here, you can just click on that point, and that means there's about 69 meters of displacement before it hits the ground. This one, if we click it right about here, this one only has 40 meters of displacement till it hits the ground. And our height right here, this one has 80 meters of displacement. So it looks like 45 degrees might give us the optimal displacement. All right. Over here, looks like 69 degrees again, or 69 meters for 30 degrees. And then finally over here, it's not too far. All right, this one only gives us about 40 meters before it hits the ground. So it kind of looks like there's some symmetry here, right? Because there's 40 here, 40 here, between 15 and 75, which makes sense because we're getting close to that 0 and 90 degree relationship. And there's symmetry here and here between 60 for 69 meters for 30 degrees and 60 degrees. And so maybe what you want to do is you want to optimize whatever your displacement is. And the optimal displacement occurs at 45 degrees. So now that's just numerically we're looking at this. And of course, we're taking numerical methods. And then we could certainly look at the Excel file, and the Excel file would tell us something similar to that. So hopefully this has been a good overview for you to be able to see how to code something that you might be able to utilize in one of your engineering or physics classes, but then also to be able to analyze it as well.